Hey guys, so part 3 of the video is dealing with orthogonal projections and reflections in space. So it's kind of drawing out all this stuff and also relating projections and reflections to each other a little bit more. So I've drawn a diagram here. We've got x, right? A vector x. We've got a projection onto v of x, a projection onto L of x. And then, we've kind of explained that this is line L and that V is perpendicular to line L. So the first thing that it explains is that if we take the projection onto V of X, that is going to be equal to this marker. So it's going to be equal to this X, right? Vector X minus projection onto L of X, because this obviously, it equals this, right? Length is preserved, right? What we've kind of already learned. So if we know that, we can just say the vector x is minus this, because as we've said, this is, another way of writing out projection onto L of x. We've already proved this. I'm not gonna, go through the whole thing again. So the next one is the reflection onto L of x, right? So if we're trying to reflect it onto this line, right, then we're going to say that's going to be equal to the projection onto L of x minus, oh wait, that shouldn't say that. I think I wrote that wrong. Yes, minus the projection V. So that means that if you subtract, right, if you subtract projection onto L of x, right, so that would be this line, and you subtract projection onto V of x, which would be this line, the two of those subtracted would be so it'd be 2 times projection onto L of x, right? Because I believe what that is referencing in the textbook is then when it goes back to reflections and it says that let's see, I think what it's done, yes. Okay, so it's taken this projection onto L of x and its projection onto V of x. And it's done that, and then it's added projection onto L of x plus projection onto V of x, which has given us the 2 projection onto L of x, right? By arithmetic. So it's subtracted these 2 things to get the reflection over L, right? Because, if we take this and we're reflecting it over L, like we're taking it and we're bringing it over here, right? So the way that we would do that would be, to subtract these 2 things, but then you go ahead, so that's for the reflection, and then you go ahead and you add, the other thing, which would be what x is, you get this first part, and then you have to subtract x, because as we know, adding, the book just didn't write the whole thing up, but as we know, when we add these 2 things, that's adding vector x plus the reflection over L of x. So it just didn't show all the steps, but that's what you get. Well, what you can then say there is 2 times x, 2 times what we know projection onto L of x is minus vector x. And then the very last thing is the reflection onto V of x. So I'm going to try to kind of erase this so we're not like muddying the waters here, and draw it out a little bit more. So in this case, what will be happening is, so if we've got the reflection over V onto x, then that of x, then that would mean that we would be taking this and it'd be reflecting it like that, right? So that's going to be V minus the projection V minus the projection L. So then once you've done that, that's going to be negative. So that's going to be -2 times what we know the projection is, because you're not subtracting V from L, you're subtracting L from V, right? And then we have, X, again, that we would have to factor in, since, as I said, this is this 2 times the projection is, when you add vector X and the reflection. So this all really just goes to show the way that you can relate all 3 of these together, which I think is cool and interesting, and also probably important later on. The other thing that this book does for this section, which I think is really helpful, is it gives an example finally that really, I think, breaks down how you actually use this. This is one of the places where I have a slight question, but it shouldn't get in the way too much. So I have this example. We have this plane. And in this plane, we've got vector 2, 1, -2. So this plane is V, and V is defined by 2x1 plus x2 minus 2x3 equals 0. So the other thing that they make sure to tell us is that the vector x equals 5, 4, -2. What they want us to find is the reflection over V of vector x. So remember that the way that we can do this is the saying that that is 2 times the projection onto x minus x, right? So the thing that they really explain to us is that we're going to take see, what are they trying to do? Okay, so we've got V, right? And so we've got V. Okay, they want to put things in terms of U, the unit vector, as we already talked about, right? So what they say is that U is equal to 1 over the length of vector V. I think this is a rule. I do not think that, the book does not really explain why this is. So I'm gonna say that this is like a rule that we have to know. But once you have that knowledge, you can really use kind of plug and chug here. So if we know that, then we can set U equal to 1 over the length of V, which would be 1 over the length of 2, 1, -2. And if we're going to use the distance formula, like I explained, that length that we're going to get is 3. So it'd be 1 over 3. So U would equal 1 over 3 times this vector V. Sorry, that was the other part that I forgot about the formula. It's that vector U equals 1 over the length of vector V times vector V. So it'd be 1/3 times 2, 1, -2 equals U. Now, this is just like a formula that they give you, you figure all that out. That all makes sense. The part that confuses me slightly is when we go to plug in the formula. So, what we're going to have to do is x minus 2 times x times u times u. This isn't surprising you. This is the formula that we already know for the reflection. What confuses me here is, so they take x, the vector x, 5, 4, -2. We already know this. I already said right here. They subtract. And here's what slightly confuses me, because you would, it says 2, right? Well, what they subtract is 2 over 9. And I'm not sure if it's some variation on this 1/3 here, because but I'm not quite sure how they got that 9. And that would be what I would have to ask Dr. Prudhomme. But for the rest of it, we've got x again, right? X 5, 4, -2 times u 2, 1, -2 times u 2, 1, -2. So yes, this is really the part that's confusing to me. I will circle it. And this is, I think, the final thing that I'm going to have to bookmark, because I think everything else from here on out is completely tracking. But I'm not sure where they got this from. And I'm not really sure what happened to this 1/3, why it's not connected to this 2, 1, -2, since that was what they defined u as. But the point is that this equals that, right? And they simplify it all the way down. They solve all of this, and they get that the reflection over V equals -306, right? So that's really just, I know there was a little bit of confusion on the exact numbers and everything, but this kind of shows how you can take this, these actual formulas and use them for real. So yeah. So I'm going to end this video here, and we're going to come back with rotations. Rotations are going to use a little bit of trigonometry, but fortunately, I think that the rotations, and from here on out, rotations, and I think what's left after that is shears, is much simpler to understand. Oh, and scaling is very simple to understand. So the rest of it should be really simple, and then I will be doing some problem set stuff, which shouldn't take too much time. So thanks so much.